In this video, we're going to talk about electric potential. And so it's what it sounds like. It's the potential for electricity to do something. So let's start with a review of potential. So last semester, you learned about potential energy. So potential energy and work. And we talked about how it related to gravity. Whenever you lift an object up, you have to do work on it. And when you do work on it, it's gaining potential energy. So now this rock at this height has a certain amount of potential to fall. And when it does, then gravity does the work and it reduces the amount of potential that that rock now has. The same thing happens with charges. To move a charge against its natural direction requires work. In the gravity example, the natural direction is to go down. So you have to do work to lift it. For charges, you have to look at what the charges are. So here we have a positive charge and a positive charge. Well, what do they want to do? They want to repel. And so to move the charge at A to the location at B, now let's draw it. So to move the charge from A to B requires work. It's going against the natural direction. These two naturally want to separate. And so if you do work on it to push it towards that positive charge, then you are giving it potential energy. So giving potential energy. Now, if that object is sitting at B and you let go, what are they going to do now? It's going to fly away because they want to repel each other. They naturally want to move away from each other, so when you let go, this positive charge will move away. So now we are losing potential energy, and the charge is now moving, so we're gaining kinetic energy, just like last semester. And just like last semester, conservation energy says that when this positive charge hits here, it will have the same amount of kinetic energy as the amount of potential energy it had here, because that potential is becoming kinetic. So if it had 100 joules of potential energy here, then here it would have 100 joules of kinetic energy. So the amount of kinetic is equal to the amount of work or potential energy it had initially. So just like last semester. Electric potential energy is the potential energy an object has due to its position. So again, just like in the previous example, we have to give this charge potential energy. We have to do work on it and give it potential to move towards that other positive charge. This results from an interaction of charges. So if you have a positive and a positive, they want to repel. That's an interaction of charges. If you have a positive and a negative, they want to attract. So here, the opposite would be if you pulled this away, then you have to do work to pull them away. Anytime a charge moves, because of the force, work is done. So it's either being done by the object or being done to the object. If you are doing work on it, it's gaining energy. If the object is doing work, then it's losing that potential energy. So where is all of this going? It's going to this idea of electric potential. Notice it doesn't say energy here, okay? Electric potential energy is one topic. Electric potential is another. Electric potential is the amount of work done per charge. So the more charge an object has, the more work you have to do to move it. So electric potential is the potential for a charge to move, is another way of thinking about it. That's not change, that's charge. R, G. Because the unit is the volt, electric potential is often called voltage. So let me make sure I underline that. Electric potential is voltage. Electric potential is voltage. So voltage is just kind of a layman's term that we use for electric potential. This is the scientific term. This is the everyday language term. And 1 volt is 1 joule of energy per coulomb of charge. So charge is measured in coulombs. So here's our first equation of the semester, voltage. So voltage is V, measured in volts. W stands for work, which can also be potential energy. And both of those are measured in joules. And Q is for charge. I don't know why, probably because C was taken, every other letter is taken, so they decided to use Q. So charge is Q, and that's measured in coulombs. I guess you can probably guess where that came from, a guy named Coulomb. So what this tells us is that the potential energy is equal to the amount of, the potential, start over. The amount of electric potential is equal to the amount of work or potential energy a charge has per coulomb of that charge. So the amount of energy per charge. Let's do some examples. If a conductor connected to a terminal of a battery has an electric potential or a voltage of 12 volts, so 12 volts, underline it, what is the potential energy of each coulomb of charge? So we want to know how much potential energy does each coulomb have. So we're given 12 volts, that's our V, so V equals 12 volts. And we have each coulomb of charge. So we're given charge. The word each means 1. So 1 coulomb. Our equation, V equals W over Q. So we're going to plug these in. So we have 12 volts equals W over 1. And so we get the amount of potential energy is 12 joules. So you can imagine if you have more more charge, more coulombs of charge, you have to do more work to have the same potential. If you have a very high potential, that means there's a lot of energy. All right, our second example says if a charge of 2 times 10 to the negative 5 coulombs, so a very small amount of charge, this is typical, has a potential energy of 540 joules, what is the voltage? So this is in coulombs, which is charge, so that's Q. Yay for random variables. So I'm going to write this in E notation to make sure that we know how to put it in the calculator. 2E negative 5 coulombs, and we have potential energy, which is equal to the amount of work done, so 540 joules, and we're looking for voltage. So V equals W over Q. So V equals 540 divided by 2E negative 5. So when we divide this out, we get a very large number, 27 with 6 zeros on the end. Another way to write that is 2.7 E7, and that's in volts. For WebAssign, you could use either one. This one might be more likely to be counted correct. And you would write it in just like this into WebAssign, just like your calculator shows you, 2.7 E7. So very large potential for this to move. All right, our last example is a balloon is charged to 5,000 volts So that's going to be our V. And the amount of charge is 1 times 10 to the negative 7 coulombs. So this is our Q. What is the potential energy of this charge? So potential energy is equal to work. So V equals W over Q. So we have 5,000. We're looking for the potential energy or work. And again, we're going to write this in E notation. 1E negative 7. So you're going to multiply by 1E negative 7 on both sides. And you're left with the amount of work of 0.005 joules of potential energy. So you can get a huge voltage, a huge electric potential on just a regular balloon, or your socks, or the clothes in the dryer. But because the amount of charge is so small, there's not a lot of energy involved. And this is why you won't die from rubbing your feet on the carpet, is because even though there's a large potential, there's not a lot of charge, so there's not a lot of energy.